video tutorial that aims to show how to use the quotient rule to differentiate a quotient function of this form. The previous few videos I've shown how to use the chain rule to differentiate composite functions. What I'm first going to do is I'm going to read through the quotient rule formula over here in the top right, talk about the components very briefly, and then how we can apply that to our examples to then get the differentiated result. I'm going to do two examples. This is the first one that we're going to work through. Okay, so over in the top right, we can see that we have our ddx, which is our differentiation operator. We have a f of x, which is a function that can be differentiated with respect to x, and the same of g of x, which is in the denominator here. So g of x cannot be equal to 0. That's just the first point that you need to keep in mind. Alright, so how do we differentiate an f of x over a g of x? Well, the quotient rule states that the result of this differentiation is going to equal the g of x, which I've written both in black here. So the g of x, that's going to be in product with the f of x function differentiated. That's why we have the prime here. And then that is going to be minus the f of x as it is in product with the g of x differentiated, as you can see the prime over in the top right. And then all of that is differentiated with this g of x squared. So we have a function y that's equal to 5x minus 2 over x squared plus 1. We can then very correctly state that this is equal to f of x, and that's divided by, one black here, g of x. So we have our top function f of x, our denominator g of x, and now we have our example, our function y, in this form. So already we can draw the connection between our example and the quotient rule. Okay, so now that we know what our f of x is in this example and our g of x, we can now look over to the quotient rule formula. We can see that we not only use a g of x and an f of x, but we also have a g prime of x, which is g of x differentiated, and an f prime of x, which is f of x differentiated. So instead of actually executing these differentiations while you're writing down the quotient, what I find easier is to go to the side and actually write each expression down, and then all you need to do then is insert that into the actual result that we can write over here. So what I mean by that is we of course know that our f of x is equal to 5x minus 2, and then if we want to get our f prime of x, which is just f of x differentiated, we know that this expression differentiated is just a 5. And we know that our g of x is equal to x squared plus 1, and therefore our g prime of x is equal, that's a 1, is equal to 2x. Now we have every component that's found in the quotient rule, so all we need to do now is insert these into the final differentiated result in that form. So we're going to do that over here. We're going to have our dy dx. So this function differentiated is going to be, the first expression is g of x, and we know our g of x is x squared plus 1. That is in product with f prime of x, which we found to be 5. We know that that's a minus f of x, which we have to be 5x minus 2, and then the last expression is the g prime of x, which we know is 2x. And then don't forget that that's all divided by g of x squared, and we know g of x is x squared plus 1. That's going to be x squared plus 1 squared. Alright, so simplifying these first two expressions in product, that's going to give us a 5x squared plus 5, and then that's going to be a minus, so we have a 2x by a 5x, which is 10x squared, and then that's a minus 10x squared, and we have a 2x by a minus 2, which is minus 4x by the minus is plus 4x, and that's all divided by x squared plus 1. And then finally, just simplifying the top part here, we have a minus 10x squared, a plus 5x squared, which is going to give us a minus 5x squared. So that's them two expressions done. And then we're left with a plus 4x, and we're left with a plus 5. And that is all divided by x squared plus 1 squared. Alright, so this is going to be example 2. If you haven't subscribed or liked the video, if you don't mind doing that now to help the channel, that would be great. So yeah, going straight into the second example here, it's a little bit more difficult. We're now dealing with trigonometric functions, but the principle stays the same, the method stays the same, so let's just get straight into it. Alright, so writing each component as we did before on the right hand side leaves us with an f of x that's equal to a cosine x squared, and then we have an f prime of x, which is f of x differentiated, which is equal to minus sine, that should be a minus 2x sine by x squared. And then we have a g of x that's equal to 3e to the x, and therefore our g prime of x is also going to equal 3e to the x, as the slope of an exponential will always be 1. Alright, so now once again we have written each component explicitly to the side, and all we have to do is fill in the formula over here on the top right. So our final dy dx is going to equal, first we're looking for a g of x, which we know is 3e to the x, and then we have an f prime of x, which we found to be minus 2x sine x squared. If you aren't sure how I got this differentiation, this was done using the chain rule, which, as I mentioned at the start, I have a video before that you can check that out after to see how I actually got this result. We have a minus, we have an f of x, which is cosine x squared, and then we have a g prime of x, which is, let's make a bit of room, which is 3e to the x, and that's all divided by g of x squared, which is going to be 3e to the x squared. The first thing that I noticed is that there's a lot of 3e to the x's around here, and I can also see that there's one that's common to the product of these two expressions, but also the product of these two expressions. So what I can do then is, when something's common to expressions such as this, we can take them out and put them as a factor. So that would leave 3e to the x. If I take that out, that will leave us with, I'll bring the minus out here, so that will leave us with a 2x sine x squared. And then if we had taken the 3e to the x out, that's going to leave us with a positive cosine x squared. So it's positive because, if you remember, I took the minus out. So if I multiplied this back in, a minus by plus would give me back that minus. And then that's all over. To make it a bit more intuitive, I'm going to write this as 3e to the x by 3e to the x. So this is just another way of writing this expression to be squared. But now we can see that we have a factor. We have a factor here of 3e to the x, and we also have 1 in the denominator. So we can actually cross this out with one of these guys here. That would leave us with a minus. Right, so this cancels with this, and what I'm going to do is I'm going to bring up the e to the x. So that's going to be e to the minus x. That's going to be divided by the 3 here. And then that's in product with what we have left over, which is 2x sine x squared, and then that's plus cosine, x squared. So that's the final result here. And just a quick note on it. We had filled out the quotient rule in this line, this dy dx here, what we noticed was that there was a common factor, which was the 3e to the x, which we then took out to be in product with the rest of the expression. We noticed that there was the same factor in the denominator, so we could cross them two expressions out, and what that left us with was the minus here. And then what I did is I brought up the e to the x that was left over, and we know when we bring up something to the power changes sign. And then we still had that third that I left here. So that left us with a minus e to the minus x over 3, and then it was just the rest of the equation here, the sine and the cosine, giving us our final answer. There are two examples. I hope you found them useful. If you enjoyed the video, if you found it useful and would like to see the subsequent videos, I'll be doing other ones on the product rule, which will be next. I've done the chain rule and a few others, so a like and a subscription would be much appreciated. And yeah, I'll see you in the next video.